All right, and welcome back, everyone. It's my pleasure to introduce Oskar Schiller from University of Hamburg, who will speak to us today about extrinsic generalized geometry. So please, Oskar.
Okay, thank you very much for the invitation. Yeah, as Jeffrey introduced, I want to speak to you today about extrinsic generalized geometry, which is based on joint work with Vicente Cortés. And just to avoid any confusion, if you look this paper up on the archive, it's called exterior generalized geometry. We decided to switch the name there because we thought that extrinsic actually is the more appropriate word in this situation. Okay, at first I want to motivate what we are about to look at in the following. What we want to consider is a Lorentzian manifold because this work is motivated by looking at the generalized Einstein equation. So for a moment we consider a Lorentzian setting. Um, but actually the extrinsic geometry, the theory that we will develop is more general, as independent of the signature. Um, and in this Lorentzian manifold, we want to consider a space-like hypersurface, which of course has a unit normal vector field. We can choose any one. I assume you are all familiar with the tools of extrinsic geometry that we that are available in this situation. So the hypersurface sigma, it inherits a Riemannian metric H because the hypersurface is space-like. And then also you have the second fundamental form, which plays an important role. And just to remind you of the definition, it's given by this covariant derivative of this unit normal vector field. Um, it can also equivalently be described as the Lie derivative in the normal direction of the metric on the ambient space. Then, of course, on the hypersurface, you have, because you have this Riemannian metric, a Levi-Civita connection as well, and then all the curvature tensors with which you can work. You have some important results in this setting, and one of the most famous ones are the Gauss-Codazzi equations, and these relate the Riemann tensor of the ambient space with the Riemann tensor on the hypersurface using this second fundamental form. You have two types of equations there. The Gauss equations captures sort of the parallel part, the tangential part to the hypersurface, and the Codazzi equation captures the part where one vector is a normal vector. You obtain as a corollary from these Gauss-Codazzi equations the constraint equations for the Einstein equations. Namely, you can compute certain components of the Einstein tensor from this extrinsic geometry data that you have. Then, of course, if you want to impose the Einstein equations on the ambient space, also these components in particular have to vanish, and these equations in that sense constrain the extrinsic geometry that you may have on a hypersurface for it to be embeddable into an Einstein ambient space. Einstein in the sense that the Einstein tensor vanishes. And also, you have this result, the fundamental theorem for hypersurfaces, which tells you that the Gauss and Codazzi equations really capture all aspects of a flat ambient geometry. Namely, it tells you that if you have this abstract data, just a Riemannian hypersurface equipped with a symmetric two-form K, this data is such that it satisfies these flat Gauss and Codazzi equations. So these are the equations from before, just assuming that the ambient Riemann tensor vanishes. You can realize this data as a Riemannian hypersurface in a flat ambient space. In fact, this immersion is unique up to a point that you have to choose. So you have to relate one point of your hypersurface to one point in the ambient space, and then also an orientation. The goal is now to develop all of this theory in generalized geometry, so that we have a theory of extrinsic generalized geometry with which we can describe the constraint equations for the generalized Einstein equations. More than that, we actually want to develop this whole theory. So it's not only specialized to this one application that we have there, but it can do more. to show that it can do more, we also develop a fundamental theorem for generalized hypersurfaces, which I may talk to you about in the end. So this is what I want to talk to you about today. So at first, I will introduce the pullback of an exact current algebroid, which is a method of studying the current algebroid over the hypersurface, or in general over a lower dimensional immersed submanifold. And then I want to explain to you how this immersed submanifold inherits the geometrical structures from the ambient space. How we then can introduce the notion of extrinsic curvature in generalized geometry. How we and then I will describe the generalized Gauss-Codazzi equations, which we found. And as I said, in the end, if time permits, I will explain the fundamental theorem for generalized hypersurfaces. Okay, so let me begin with a pullback of an exact current algebroid. So just to remind you of the generalized tangent bundle, basically I assume somewhat familiarity with generalized geometry, but I will give reminders. If I am too quick in reminding you of something, please interrupt me, especially given that today the audience is not as large as usual. Feel free to just interrupt me and ask questions. The generalized tangent bundle is the direct sum of the tangent bundle with the cotangent bundle. And it has this natural inner product of a neutral signature, which is just given by contraction. And as well, it has a bracket, the Dorfman bracket, or the H-twisted Dorfman bracket, if you will, or H naught, I call it here. H naught is a closed tree form. And it is given by this explicit formula, so it is somewhat like a Lie derivative, but in this case, you have this twist appearing there, this closed tree form as well. And then you have the anchor, which is just the projection onto the vector field part. And so now we want to consider the situation that we have a submanifold in ambient manifold. And we want to consider a bit what we can do with a generalized tangent bundle over this submanifold. So canonically, we can guess that we have the structure of the generalized tangent bundle over the submanifold with the twisted bracket, where the twist is now given by the projection of H naught into the tangent bundle of the submanifold. But we want to so the tangent bundle of the submanifold, you can canonically understand as a subbundle of the tangent bundle of the ambient space. And we want to achieve a similar thing for the generalized tangent bundle. However, this is not, in order to do this, you have to make a choice. So you can see this because in order to include the cotangent bundle, I view it as a subbundle of the cotangent bundle over the ambient space, you have to choose a transversal bundle, because then you can identify the cotangent bundle canonically with the annihilator of the transversal bundle. So we can see that the transversal bundle is somehow the data that we have to fix, but in generalized geometry, these B-field transformations are very important, so we have to somehow develop a notion which is more general and incorporates that B-field transform, the symmetry under B-field transformations in a way. And so the notion that we developed to deal with this is the notion of a Courant transversal bundle. The Courant transversal bundle is a subbundle of the generalized tangent bundle over the ambient space, restricted to this submanifold. And it is such that the sequence that you see there is a short exact sequence. So what this means is that in the right splitting, the Courant transversal bundle actually is the direct sum of the transversal bundle with the annihilator of the transversal bundle. But only in the right splitting, so you can consider more general Courant transversal bundles than this direct sum. They are just transformed by a B-field transformation. We are interested in this Courant transversal bundle because given this Courant transversal bundle, we can now canonically identify the generalized tangent bundle with the orthogonal complement of the transversal bundle, which we will call En. So not to be confused with the restriction of the of E, the generalized tangent bundle over the ambient space onto the submanifold. And what we show is that this bundle naturally inherits the structure of an exact current algebroid from the ambient current algebroid. So the inner product is just given by restriction, or you can define via restriction. You can also define the bracket, not directly via restriction because you have to work with extensions technically to make everything work, but this actually works. So yeah, you extend the sections to the sections of the ambient space, then you employ the bracket of the ambient space, and then you can project the result. And similarly, you can define the anchor just via restriction. And this actually is a realization of this canonical structure that we looked at before. So it is isomorphic to the tangent bundle, the generalized tangent bundle over the submanifold, equipped with this bracket given by the where the twist is given by the parallel projection of H naught. And why is this called the pullback current algebroid? There's no pullback involved here. This is because it is a concrete realization of the pullback current algebroid, which was defined previously by Burston, Cavalcanti, and Gualtieri. They define a similar object just via a quotient bundle, via a quotient construction. And because it is a quotient construction, they have no way of viewing the quotient as a subbundle of the ambient space. But we find that it is very convenient, and especially in calculations, to have this realization as a subbundle of the ambient space. And this is what we provide with the definition that we give here. And now that we have this nice realization of the current algebroid over the submanifold as a subbundle, we can easily talk about the inheritance of geometrical structures. So, okay, so here I will give you a quick reminder of the relevant geometrical structure. Please interrupt me if I'm going too quick or too slow for that matter. So a Riemannian generalized metric is a positive definite symmetric bilinear form over the generalized tangent bundle. That much you might have guessed. And then it has this compatibility condition with the inner product. So if you raise an index, if you will, of the generalized metric with the inner product you have on the generalized tangent bundle, then you get an endomorphism. And this endomorphism you ask to square to the identity. And you can write, in general, the generalized metric in the case of exact current algebroids, in this form. So it is related to a normal Riemannian metric in this setting. If you allow for more generalized metrics, then the associated usual metric just has the appropriate signature. And also, you need a two form to describe this metric. Yes, in this way. So a generalized metric is always associated to a normal metric and a two form. And a generalized metric also gives you a preferred identification of your generalized tangent bundle with a generalized tangent bundle with a specific twist, if you will. So it gives you a preferred splitting for those who are more familiar with the subject. And this splitting is precisely the splitting in which the generalized metric then becomes one where the B field is set to 0. So without loss of generality, you could assume in this talk that B is equal to 0. But I will, for completeness, keep the B in the equations where it appears. And then another very important object is a generalized connection. This is similarly to a usual connection defined as a derivation which satisfies a Leibniz rule, namely the pi Leibniz rule. So the Leibniz rule is modified by the anchor, and you also ask for compatibility with the inner product. A generalized connection is then called Levi-Civita if it preserves the metric and if it is torsion-free. And it is well known that such generalized Levi-Civita connections always exist, but they do not exist uniquely. And to resolve this issue of non-uniqueness, divergence operators were introduced. And these are differential operators from the space of sections of the generalized tangent bundle to the space of real-valued functions over the manifold. And they also satisfy a pi-Leibniz rule, which is without the pi, the Leibniz rule that you can check a normal divergence operator satisfies. And what you can see is that both a generalized metric and a generalized connection define divergence operators in a canonical manner. And what you want to allow for is for the divergence operator to describe a different degree of freedom than the generalized metric. And so you will want to assume that the divergence operator generally is not the divergence operator induced by the metric. And the difference between these two objects you can describe by a section of the generalized tangent bundle, and this section is called the dilaton. So the space of divergence operators is an affine space over the space of sections, so this difference always defines such a section of the generalized tangent bundle. And still, even if you ask for compatibility of the Levi-Civita generalized connections with a divergence operator, these generalized connections are not unique. And it has been known in the literature for a while that there's a canonical choice for a connection in this setting. But we were not content with there being a canonical choice. We wanted there to be a reason to work with this canonical choice. And so we found that there's a condition which selects this particular connection. So it is, in this sense, a preferred connection to work with. This will be of some importance to the generalized fundamental theorem for hypersurfaces, which I will at least give a brief mention. Okay, now that we are all familiar again with the geometric objects of generalized geometry, let me explain to you how these are inherited over a submanifold. So a specific choice of Courant transversal bundle is the Courant normal bundle if you have a generalized metric and a submanifold, which is such that if you have a semi-Riemannian submanifold, meaning that the metric that the submanifold inherits is not degenerate. Okay, and this Courant normal bundle is just given by, so you apply this isomorphism, this automorphism to this construction nu plus g nu, where nu is the normal bundle for the metric G. So for those who are more familiar with generalized geometry, you have, of course, to make use of a splitting in order to include this construction normal bundle plus annihilator of the normal bundle, which in this case you can write as G nu into the Courant algebra, the exact Courant algebra with which you are working, which is why the F appears in that equation. Okay, and then you have a preferred realization of this bundle En that I explained to you before as the orthogonal complement with respect to the Courant normal bundle. And now we can define in a very straightforward way the inherited data, the data that En inherits. So you have this tuple, generalized metric divergence operator, generalized connection on the ambient space. And then you can define an inherited generalized metric simply by restriction. You can check that this actually defines a generalized metric. Then you can define an inherited divergence operator in the following way. So you have this inherited generalized metric, which gives you a divergence operator, as I explained before. And then from this, you subtract the parallel projection of the dilaton and you use the inner product to turn this into a section of the dual space. So this makes this definition might appear somewhat arbitrary, but it makes sense because in the special case of exact divergence operators, you can realize divergence operators as a volume form. And then this divergence operator that we define here is just the restriction or, or if you have the volume form for the divergence operator on the ambient space, you can insert the normal vector into that, and then you get a volume form over the or not a normal vector if a normal vector only if it's a hypersurface. Otherwise, of course, a basis for an orthonormal basis for the normal bundle into this volume form, and you get a volume form over the submanifold. This is then the divergence operator associated to the divergence operator that we define here. That is the motivation for that definition. Also, you can define an inherited generalized connection. Again, here you have to work with extensions of the sections of the exact current algebroid over your submanifold to sections of the exterior exact current algebroid of the ambient manifold, and then project the result. And what we also
Oscar,
prove,
can you
yes,
remind me, what is the map eta again? Sorry, can you just repeat?
the eta is the inner product.
Well, that's just the neutral inner product on N.
Yes, yes.
Oh, okay. Yeah. Oh, okay. Yeah. Thank you.
Okay. Otherwise, maybe I should give a moment for anyone to ask questions. Okay, doesn't seem to be the case. Okay, and we proved that this construction is a nice construction and that it preserves many important properties. So, as I explained or reminded you of, a generalized metric is associated to a metric and a B field. The generalized metric that is induced over the submanifold is just the generalized metric that is associated to the inherited normal metric and the tangentially projected B field. Furthermore, if the divergence operator on the ambient space was exact or respectively closed, I didn't tell you what this is, but okay, these are important properties for a divergence operator. Then these properties are preserved, and the inherited divergence operator is again exact or closed. Also, if the generalized connection on the ambient space was torsion-free, then the generalized connection over the inherited generalized connection is torsion-free as well. And if it was metric, then the inherited connection is metric as well, with respect to the inherited metric. However, this compatibility does not in general extend to divergence operators, or the preservation of the compatibility does not extend to this case. So if you have that the generalized connection on the ambient space is compatible with a given divergence operator, then this does not mean that the divergence operator associated to the inherited connection coincides with the inherited divergence operator. So I will say a bit more about this. You can't always achieve this to be the case. So within the space of generalized Levi-Civita connections compatible with a given divergence operator, there always exists a choice, and this is also not unique in most cases, but there exists a choice of generalized connection for which the equality, the compatibility is preserved under this process of inheritance. But you have to be careful with this. This is what this tells you. In particular, a consequence of this is that the parallel projection, if the parallel projection of the dilaton is non-zero, so this is when these problems can arise, then the canonical connection that I told you about before does not, here I forgot some brackets. So I mean, of course, that if you have the canonical connection on the ambient space, and then you consider the inherited connection, so there should be around this brackets and then an n to indicate that you consider the connection that it induces over the submanifold. This does not equal, in that case, the canonical connection that you get from considering the inherited metric and the inherited divergence operator.
Sorry,
Yes.
I think I think I missed the point. You're saying it induces these three pieces of data, like a metric, a divergence operator, and a connection.
Yes.
That the divergence operator associated to the induced connection is not the same as the divergence operator as the
In
induced
general,
divergence operator. That's what you're saying?
yes, in general. But I'm also saying that there's a way of resolving this. So this is not like it's there's a good reason for this, and we know how to deal with it.
Okay.
Okay, so is there because there always exists a choice of remember that these generalized derivative connections with given divergence are not unique. There always exists a choice for which the
Oh,
equality
oh, oh.
so for which the preservation the compatibility is preserved.
I see. Okay, yeah. Thank you. Yeah.
Okay. Okay. And now knowing about this inherited geometry, we can define generalized extrinsic curvature. Okay, so just to give you a picture for a moment of what we're doing. So we're considering this ambient space, and now we actually want to consider the situation that the submanifold is a hypersurface. This will simplify many things for which we want to do. Um, and then, well, to describe the initial data for the generalized Einstein equations, so it's a slight tangent on which I'm going. The generalized Einstein equations are second-order equations. So to describe the initial data, you have to describe the initial values of the fields on an initial hypersurface and their first time derivatives. That much you can guess. And to describe these first time derivatives, if you're familiar with the normal Einstein equations, you can use the second fundamental form. The second fundamental form, as I reminded you about, is the first derivative, the first time derivative of the metric. And now in our case, we just have the difference is that now instead of the tangent bundle, we're working with the generalized tangent bundle, and we have sort of two normal directions. We will choose two special ones. I will explain this in a moment, n plus and n minus. And with respect to n plus and n minus, we can define a generalized second fundamental form and a generalized mean curvature. And we will actually find that this data taken in total can be used to describe the initial data for the generalized Einstein equations and the constraint equations as well. Okay, so a bit more of a reminder. We have to recall that the endomorphism associated to the generalized metric, because it squares to 1, has eigenvalues plus minus 1. And these eigenvalues, you have the associated eigenspaces, E plus and E minus, which are very important in generalized geometry. These are given as stated there, and the important thing that we want to keep in mind as well is that they are both isomorphic to the tangent bundle, and the anchor describes the isomorphism. So they are isomorphic as vector bundles, of course, to the tangent bundle. And you have this eigenspace decomposition with this, which is orthogonal with respect to the generalized metric and the inner product. I should also say, if you consider the current normal bundle and that we defined this En, the exact current algebroid over the submanifold as the orthogonal complement of the current normal bundle within the within the current algebroid of the ambient space, they are taking the orthogonal complement. If you work with the current normal bundle, it does not matter whether you choose the generalized metric or the inner product. So this is also very convenient for calculations, I wanted to stress. But okay, and here this is the case as well. This is orthogonal with respect to both the generalized metric and the inner product. Now we consider a Riemannian hypersurface with unit normal n in the ambient space. And we want to describe this current normal bundle a bit more specifically. And by definition, it is given by the span that I written down there. But we want to rewrite these basis vectors somewhat, namely in terms of vectors which are in the eigenspaces E plus and E minus respectively. And the precise formula is given as there. So it is the normal vector plus the normal vector inserted into the B field plus minus the normal vector inserted into the generalized metric. And okay, so just to remind you of the notation there, this of course means that this n inserted into the B field and n inserted into the metric are one forms. And as I described before, you can also forget about the B field, if you will. You can turn that off, and then it's just n plus minus gn. Okay, and now we, with this, define the generalized second fundamental form as the covariant derivative. And so we get two generalized second fundamental forms, one for each choice of normal vector. And we define them as the covariant derivative of this normal vector that we choose. And then we use the generalized metric in order to turn this into a bilinear form. And in addition to the generalized second fundamental form, we get one object which we are not familiar with from submanifold geometry from the ordinary version, which is the conormal extrinsic curvature. And it is defined by taking, again, a covariant derivative of these normal vectors, but now with respect to this linear combination of n plus and n minus. So recall that by the definition of n plus and n minus, if you take the difference of these two vectors, you get 2 times gn, so n inserted into the metric, which is a one form. And so if you project it with the anchor, you get nothing. But in the Leibniz rule, which the generalized connection obeys, is the pi Leibniz rule. And because of this, this means that if you take a covariant derivative in a direction that is a covector, then it's not actually a derivative. It's a tensorial operation. It's a contraction with a tensor. So this derivative that we write down there does not depend on an extension of the normal vectors onto the ambient space. Which is why this is well defined and important to keep track of. So to immediately answer the question, what the relevance of the conormal extrinsic curvature is. So if you want to have an interpretation for it, what we prove is that for a Levi-Civita generalized connection which is compatible with a given divergence operator, the vanishing of these conormal extrinsic curvatures is equivalent to the compatibility of the induced divergence of these induced operators over the hypersurface. Okay, and we also prove that, as I said, you can always find a connection for which these conormal extrinsic curvatures vanish, if you will. Okay, just I want to give you formulas for these objects that we define here. To give you these formulas, I have to remind you of another thing, which is that every Levi-Civita generalized connection compatible with a given divergence operator can be written as the sum of this canonical operator that I told you about before. With some difference tensors, because the space of Levi-Civita generalized connections is similarly to the space of normal connections in a fine space over some vector bundle. And this vector bundle I had written down there in more detail. If you want to be precise, it's a subspace of the generalized first prolongation of SO of E plus minus. This is a subbundle of this bundle that I've written down there. And what we prove is that, which will be relevant in a moment, it's a small lemma, is that by insertion of the normal vectors n plus minus into such a difference tensor, you can obtain any trace-free endomorphism over E sigma plus minus, over these plus minus one eigenbundles of the generalized metric in the current algebroid over sigma. So this map that I've written down there, in other words, this map is a surjective map. Okay. And with this, I can give you the formulas for the generalized second fundamental forms. To give you the formulas, we use this identification of these plus minus one eigenbundles with the tangent bundle. This is just used to make the formulas more legible, because then we can describe the objects living on the exact current algebroid just via objects, via normal tensors living on the hypersurface. And then we obtain these formulas. So the first formula is a formula for the pure type components. And you see that the generalized second fundamental form is related to the normal second fundamental form. Then this difference tensor appears there. You also have a contribution by the dilaton, and finally a contribution by the twist H. And the formula for the mixed type components is a bit more simple. It's more straightforward. And there's a reason for that. I will say a few words about these objects in a moment. So it only has a contribution of the second fundamental form, and then the normal part of the twist as well, just with a different factor. And finally, for completeness, it will not really be relevant. There's also a formula for the conormal exterior curvature. Okay, and there's this var epsilon appearing in these formulas. It is always to deal with different signatures. So if you just focus on the Riemannian case, it's +1. If in the Lorentzian case, the normal vector is assumed to have norm -1. Okay, and the mixed type components actually satisfy another nice formula, which is reminiscent of this formula of the second fundamental form that you obtain via the Lie derivative. So if you use the Dorfman bracket in order to form this derivative of the generalized metric, then you get the sum of these two mixed type components of the generalized second fundamental form. Okay, and now let me tell you a bit about the interpretation of these formulas, especially given that we have this difference tensor appearing in them. So if you are interested in this from a physics point of view, so the generalized Einstein equations are equivalent to the equations of motion of the bosonic sector in type 2 10-dimensional supergravity, and the Neveu-Schwarz sector of that. So these words don't have to mean anything to you, but the relevant information right now is that if you are interested in this from this perspective, then the dynamical objects, the objects that really encode your degrees of freedom, are the generalized metric and the divergence operator. The generalized connection really is an auxiliary choice. But it does not, which choice you make does not encode any physical information. And then this difference tensor that appears in these equations, it does not contain any physical information. And for this reason, it is relevant what I told you about before, that with this chi plus minus perp, we can actually realize any trace-free bilinear form over E sigma plus minus. And so if you want to extract from the pure type components, that part which is independent of the difference tensor that you choose, you have to take the trace. And this gives you the generalized mean curvature. So I will give the formula on the following slide, but before I switch to that slide, I want to stress again the mixed type components, on the other hand, are immediately independent of the choice of this generalized connection. This has to be the case, as you can see from the formula that I give you on the bottom of the slide, because there we really just take with a Dorfman bracket the derivative of the generalized metric. There can be no contribution of the choice of generalized connection which you make. Finally, I want to say that also, of course, if you from another perspective than this physical perspective that I gave you right now, you can assume a more mathematical perspective where you say, well, we have proven that there is this preferred choice of generalized connection, and this preferred choice, of course, corresponds to the case that the difference tensor just vanishes. And if you adopt this standpoint, then all components of the generalized second fundamental form, as well as the co-normal extrinsic curvature, are relevant. And you just use the formulas with the difference tensor set to 0. Okay, so these are the two philosophies that the two viewpoints that you can adopt here that are of relevance. Okay, so as I told you, as I explained to you right now, the generalized mean curvature is the part of the pure type components of the generalized second fundamental form, which is independent of the choice of generalized connection with given divergence. Generalized Levi-Civita connection should, of course, be written there. And so you take this trace, and what you obtain is the mean curvature plus a modification due to a normal part of the dilator. And okay, you obtain two generalized mean curvatures, but in relevant situations, these actually agree, and you can forget about the fact that there are two of them. In particular, this is the case if you have an exact or closed dilaton, and it does not even need to be closed, it just has to be given by a one form. This is still just a special case, but okay. Then these two generalized mean curvatures actually agree. Any questions so far? And how much time do I have?
I mean, I guess until the hour, so maybe 12 more minutes.
Until the hour. Okay. Okay, great. Okay, just to remind you of generalized curvature. So given a generalized connection, there's well-known by now definition of a generalized Riemann tensor, which is reminiscent of the normal definition of the Riemann tensor. There's some subtlety going on with the dot, dot, dot there, but okay. And then from that, you can obtain a generalized Ricci curvature and the generalized scalar curvature by taking the trace with a generalized metric. Again, this will be relevant for the generalized fundamental theorem for hypersurfaces. Now, given this preferred choice of generalized Levi-Civita connection, you can study the generalized Riemann tensor associated to this preferred choice. And we did this, and we found that generalized Riemann flatness, in the sense that this preferred choice of Levi-Civita connection vanishes, is in fact equivalent to complete triviality. So the normal metric associated to the generalized metric has to be flat. The effective twist has to vanish. And the divergence operator has to just be the metric divergence operator. This will be relevant later, but okay. Okay, to go back to generalized extrinsic geometry, we have the generalized Gauss-Codazzi equations. So in order to derive them, it is useful to first establish the generalized Gauss and Weingarten equations. And these describe the covariant derivative of so if you take sections of the exact current algebroid over the hypersurface and use the generalized connection from the ambient space to form this covariant derivative, then you can decompose that in terms of the covariant derivative of these sections using the induced connection over the hypersurface, and then a contribution in the normal direction due to the generalized second fundamental forms. You just have now two contributions there because you have these two normal vectors. And so you sum over them. This is meant by the sum over the signs plus minus. And then with them, you can establish the generalized Gaussian-Kodazzi equations, which we do. Again, these relate the generalized Riemann tensor of the ambient space with the generalized Riemann tensor of over the hypersurface. These equations are quite lengthy, but they are reminiscent of the normal Gauss-Kodazzi equations, and yeah, you can work with them. You have more equations because of this issue that I hinted at before, with the special linear combination of n plus and n minus giving you the co-normal vector, which if you take a derivative in the co-normal direction, this is not an actual derivative if it's a covariant derivative. For this reason, also these components do not depend on the extension of the normal vector onto the ambient space, and can be described and captured in Gaussian-Kodazzi equations. And tracing over these generalized Gaussian-Kodazzi equations, you obtain the constraint equations for the generalized Einstein equations. There again, on the left-hand side, we have up to a factor the generalized Einstein tensor, if you will. So this linear combination of the generalized Ricci tensor with the generalized scalar curvature. And these equations are structurally exactly the same equations as the normal constraint equations for the Einstein equations. This is the beauty of these equations. There are, of course, more pluses and minuses appearing there, but for example, with the generalized mean curvature, I explained to you that in the physically relevant setting, you actually have that both of these are equal. So this averaging that you have in the first equation over the plus part and the minus part, this just gives you the generalized mean curvature. Otherwise, the constraint equations are exactly the same constraint equations that you get in the ordinary setting, just with the ordinary objects replaced by the generalized objects. And these are equations really for the pair which relate objects determined by the generalized metric and the divergence operator on the ambient space, and then this induced extrinsic geometry over the hypersurface. And as you can see, there's no dependence on a choice of a specific generalized connection, which makes sense because, as I told you about before, the generalized Einstein equations are related to the supergravity equations, in which, also for the Einstein equations as well, the choice of generalized Levi-Civita connection is only auxiliary in order to describe them. And so it makes sense and has to be the case that also for describing initial data and the constraint equations, no choice of generalized connection has to be made. Okay, and to compare this with, you can of course decompose these equations into equations in ordinary terms, and then they look like this. So they are way longer and structurally way less pleasing, with all sorts of contributions which you have to make sense of. So I think the right way of studying these equations is in the language that we provide in this paper. Okay, and then I actually have 5 minutes to explain to you the fundamental theorem for generalized hypersurfaces. So for the fundamental theorem for generalized hypersurfaces, we consider an arbitrary admissible arbitrary admissible extrinsic geometry. What does admissible mean in this context? So it's at the bottom of the page if you're looking for an explanation. It just means that these objects satisfy the relationships which are necessary for being induced by data coming from a generalized metric, a divergence operator, and then crucially the canonical Levi-Civita generalized connection. And because the fact that you make a specific choice there, the canonical connection, this implies some relationships for the extrinsic geometry. And for this theorem to make sense, you have to ask for the extrinsic geometry to satisfy these relationships. Um, and furthermore, the tuple not only has to be admissible, it also has to satisfy the flat generalized Gaussian-Kodazzi equations. And we want to prove that these equations are, again, not only necessary for the data to come from a flat ambient space, but also sufficient. And we find this, in fact. So you, again, get a hypersurface immersion, which actually satisfies the same uniqueness properties as the hypersurface immersion of the ordinary theorem. Then you can realize the data as this hypersurface immersion into the untwisted generalized tangent bundle over flat space. Because the ambient space is then untwisted, you can go back to the formulas for the generalized second fundamental form and so on. And you can see that, for example, the generalized second fundamental form just reduces to the second fundamental form because all of these extra contributions by the dilaton and by the twist, they have to vanish in this case then. In this setting, the generalized Gaussian-Kodazzi equations reduce to the ordinary Gaussian-Kodazzi equations, the flat Gaussian-Kodazzi equations. And so in particular, you get this data, the hypersurface equipped with a Riemannian metric and the second fundamental form, which satisfies the flat ordinary Gaussian-Kodazzi equations. Okay, and then I can also give you an idea of how we achieve this proof. So essentially, the idea is that we know that the result has to be true because we know that if you have we have this trivialization result that if the generalized Riemann tensor vanishes, the generalized Riemann tensor for the preferred connection, then you have this complete triviality. You get flat space and everything. If the generalized Gauss-Kodazzi equations that we have actually encode generalized Riemann flatness of the ambient space, then we know a priori that we will have to reduce to the situation where we just have an ordinary, where we just satisfy the ordinary flat Gauss-Kodazzi equations. And because of that, we will be able to apply the fundamental theorem for hypersurfaces, the ordinary one, to recover the generalized version. The problem is that we do not a priori have access to the generalized Riemann tensor of the ambient space. This is precisely the ambient space that we want to construct for our theorem. And to overcome this, we construct several synthetic objects that act like an ambient space without fully constructing the ambient space directly. And so at first we construct a version of the canonical connection, a synthetic version. And this synthetic connection, to be specific, has to be in E sigma plus L connection on E sigma plus N. So L, and there's this is a synthetic co-normal bundle, and N is a synthetic normal bundle. It has to be a connection of this type because you have to, in the direction entries, allow for directions which are co-normal for the reason that I mentioned several times before, that you have the pi-Leibniz rule and the co-normal under the anchor vanishes. And it has to be on E sigma plus N because this is actually to be expected because, of course, the connection that we want to replicate here is a connection on the ambient space. And so to replicate the ambient space, we add this synthetic normal bundle. Then we show that this synthetic connection, the synthetic version of the preferred connection that we construct there, satisfies several properties of this canonical connection. So in many situations, it basically acts in the same way. And we also show that you can then associate to such a connection a generalized Riemann tensor. And this generalized Riemann tensor you can immediately see has to vanish by the generalized flat Gaussian-Kodazzi equations. And then all that remains is to extend this Riemann tensor associated to this synthetic connection to the synthetic ambient space. And then you can actually check that the trivialization result that we have applies in this situation, because it really does not require you to work on an exact current algebroid. It is sufficient to work on data that is defined over a one jet. And because we have enough control to describe everything that we need on the one jet over a point, we can apply the result, obtain complete triviality, and apply the classical fundamental theorem for hypersurfaces to obtain our result. So thank you very much for your attention.
Thanks, Oscar. Are there more questions? I guess I was curious if so you derive these like constraint equations. Does it again imply that the scalar curvature is positive in the generalized sense?
You mean sort of like a positive mass theorem, or what are you?
Well, more like sort of dominant energy condition, which would
Dominant.
then imply
Yeah.
positive mass theorem.
So I don't then necessarily mean what you know by that it implies that the scalar curvature is positive. I mean, the dominant energy condition is a condition that you have to require. But
Oh, okay.
um,
Yeah, sorry, right. It's not implied by this. Can you go back to the constraint equations that you have?
yes, of course. Should be these.
So I guess, yeah, it's like you're setting the left-hand side to 0, but
Exactly. So these are the necessary conditions for the data to
sorry, yeah,
be
of course. Yeah.
embeddable uh, into an ambient space which satisfies the generalized Einstein equations. And the question if the initial value problem is well posed is precisely the question if these equations are also sufficient,
Right,
if you will, for the data to be embeddable.
right. Okay. Yeah. Um, Other questions? Okay, well, if not, let's thank Oscar again for the nice talk. Yeah.
And thank you again for the opportunity to give this talk to you today.
Mhm.